All right, so in this video, we are going to jump into some of the trends in the periodic table. And the first one that we're going to take a look at has to do with the electrons, specifically the valence electrons. And we're going to focus on the main group or the representative elements. So for the main group or the representative elements, and remember these belong to groups 1, 2, and then 3 through 8. What we're going to see is that the elements that belong to the same group have the same number of valence electrons. All right, so all of the trends we're going to list here are going to be trends belonging to the main group elements. So for the elements that belong to the same column or the same group, they have the same number of valence electrons. And when we look at the elements that belong to the same period, remember period is the row, what we're going to see is that the number of valence electrons increases from left to right across the table in a periodic fashion or in a predictable fashion. All right, we're going to take a look at some of these examples here in a little bit. So let's first of all take a look at one particular column or group, which we call the noble gases. So we need to know the names for these different groups and also which group number they correspond to. So the noble gases are the group 8A elements. And they're all going to have 8 valence electrons, every single one of them, with the exception of one, which is helium, the very first one, which only has 2 valence electrons. All right, so if you look at the electron configuration, specifically for the valence shell for the group 8 elements, you'll see all of them have 8 valence electrons in their outermost shell. That's the valence shell. And helium doesn't have 8 because its valence shell is the first shell, and that can only accommodate 2 electrons. So what that means is their valence shell is completely full. With electrons. And as a result of that, that leads to extremely high stability. So these are very stable elements. Okay, and as a result of that, they are also very unreactive. So they really don't want to combine with anything else. They are pretty much happy. They're very happy, actually, being on their own. Another term that you'll see for unreactive or inert, or noble, you'll see the term inert. And inert means unreactive. So you'll see noble gases or inert gases, they mean the same thing. Now, these noble gases are the epitome of stability on the periodic table, and all the other elements actually want to be like them. So all the other elements want to be like the nearest noble gas to them. And this is really important because it dictates how these other elements are going to behave. And they want to be like the nearest noble gas in terms of their electrons, right? That's the important subatomic particle. And the reason is so that they can become more stable. Stability is a driving force for lots of chemical reactions. Okay, so if you keep that in mind, the rest of this chapter, but also the next chapter, is going to make a lot more sense. All right, so that's the group 8A, the noble gases, their valence electrons, and their reactivity or lack thereof. So let's take a look now at going on the other side of the periodic table, the left side of the table, where the metals are found. And as you've seen in our overall view of the table, metals make up the vast majority of the elements on the periodic table. We'll first of all take a look at the group 1A elements, and these are collectively known, that first column, that first group, we call these the alkali metals. And they all have one valence electron. Right, because their configuration ends up being NS1, where N is the principal energy level. So these elements, the group 1, all have one valence electron. So the group number is actually going to tell you how many valence electrons these elements are going to have for the main group elements. So how do these become more stable? Well, they become more stable by losing that one valence electron. I'm going to abbreviate valence as VAL. And as a result of that, if you take away a negative charge from something that's neutral, you end up forming a positive ion, which we call a cation, which we've talked about previously. And that cation is going to have a charge of +1. So for example, we can say that sodium, being in group 1, it's an alkali metal, is going to lose that one valence electron, and it forms Na with a positive charge, or a +1. You can put the 1 in there as well. All right, and that's going to be the case for all of the group 1A metals. That is how they're going to behave. They want to become more stable by losing that one valence electron. The group 2A elements, these are collectively known as the alkaline earth metals. And their electron configuration, their valence electron configuration ends in NS2, where N is a principal energy level, so they have 2 valence electrons. Okay, they're in group 2, they have 2 valence electrons, and they are going to become more stable by losing those 2 valence electrons. And as a result of that, they're going to form a +2 cation, or a cation with a +2 charge. So for example, magnesium in group 2 will lose 2 electrons to become more stable, to be like the nearest noble gas, and we end up forming Mg with a +2 charge. All right, so that's the group 1 and the group 2, the alkali metals and the alkaline earth metals. We mentioned that the metallic elements make up the majority of the elements in the periodic table. Out of those, a lot of them are found in both the transition and the inner transition block of the periodic table. Remember, the transition and the inner transition metals, these are located in the middle, that big depression in the periodic table. That's where the transition metals are found. And then the inner transition metals usually are shown underneath, in those 2 rows underneath the periodic table. So these, the chemistry of these transition and inner transition metals, they become a little bit more convoluted. They tend to lose electrons from both the s and the d orbitals. So sequentially, they lose electrons from the s first, and then the d orbitals to form cations. So again, they're going to form positive ions when they try to become more stable. And then your metals that are found in the p block, so there are some p block metals, these are going to lose electrons from both the s and the p orbitals to form your positive ions, or cations. Okay, so overall, what we can say is your metals tend to lose electrons to become more stable, and as a result, they form positive ions, which we call cations. Right, and the reason for this is so that they become more stable. They want to have the same electron configuration as the nearest noble gas to them. All right, so let's take a look now at the metalloids and the nonmetals. So the metalloids, which are often referred to as the semi-metals, we talked about this at the start of the chapter. These are located along that zigzag line, or the staircase, on the periodic table. It's a very thick line that you can see. And these the properties of the metalloids are intermediate. They're sort of in between the metals and the non-metals, just like their location, right? Their location is indicative of their properties. So for example, like silicon, which is a metalloid, instead of being a good conductor like metals or a non-conductor like non-metals, it tends to be a semiconductor, sort of in between. Right, and that's used in a lot of electronic devices. So there are a couple of things that metalloids can do to become more stable. They can either lose electrons from the p and then the s orbitals to form cations, or they can do the opposite. They can actually gain electrons to form anions, which are negative ions. Okay, so the chemistry of the metalloids tend to sort of span the chemistry of both the metals and the non-metals, because that's kind of what they do, right? They are in between the metals and the non-metals. The non-metals, in comparison, right, these are located on the right of the periodic table, and specifically to the right of the zigzag line or the staircase. So how do your non-metals become more stable? Well, they do the opposite of the metals. They tend to gain electrons, and by gaining electrons, by gaining negative charges, they will form negatively charged ions, which we call anions. Okay, so metals tend to lose electrons to form positive ions. Non-metals gain electrons to form negative ions, which we call anions. So let's take a look at a couple of these specific groups or columns on the periodic table. Well, first of all, take a look at the group 7 elements, which are collectively known as the halogens, or halogens if you want to pronounce it that way. Okay, so because they are in group 7, okay, the group number is going to tell us how many valence electrons they have. They're going to have 7 valence electrons, and their electron configuration, their valence electron configuration, to be more specific, is going to look like this. It's ns2, so 2 electrons in the highest energy level, and then np5, so 5 electrons in that p sublevel, 2 electrons in the s sublevel for the highest energy level. So if we add these together, we get 7 valence electrons. So for example, if you look at fluorine, right, these are just the valence electron configurations in the outermost shell. You see fluorine here has 5 p electrons and 2 s electrons, so that gives 7. And that's the case for all of these over here. So in order to be like the nearest noble gas to these, right, we said the noble gases all have 8 valence electrons. So for these halogens to become more stable, right now they have 7 valence electrons. They want to have 8. The easiest way to do that is to gain and to gain 1 electron to become more stable. As a result of that, they're going to form anions or negative ions, and that ion in this case will have a -1 charge. So for example, fluorine, being in group 7, will want to gain 1 electron, and it will form F with a -1 charge. You can write the 1 in, or you can just leave the negative sign. So we can use our periodic table as a guide for several things. We've seen that metals form cations, and they form cations by losing electrons, specifically the valence electrons that are in their atom. What we will see eventually is that the transition, the inner transition, and the p-block metals, they tend to form a variety of charged cations, which are positive ions, by the way, as a reminder. Okay, so we refer to these as variable charge metals. Meaning their charges are not fixed when they form ions. And as an example of this, iron, Fe, can be Fe2+, or it can form Fe3+, and it just depends on how many electrons it's being, or it is giving up. Right? And we'll see that as we get into the next chapter. So metals lose electrons, form positive ions. Non-metals form anions, which are negative ions, and they do so by gaining or accepting electrons. So the periodic table is helpful to us in determining the charges on these ions, because the group numbers actually are going to be helpful. So for example, and again here we're looking just on the left 2 columns and the right 6 columns. Those are our representative elements, or the main group elements. So if we look at, for example, the group 1A elements and the metals specifically, they all form a +1 charge. The group 2A all form a +2 charge. There's a typo on this, by the way. Hopefully this is not also in your textbook. Mg should be +2, calcium is +2, strontium +2, barium is +2. So all the group 2s form a +2. And then the group 3 metal that we're concerned with here, aluminum, is a +3. So we can say then, for the representative metals, and this is the quick way to determine this, the charge is simply equal to the group number. And it's a positive charge, right? Because metals form positive ions. So just by looking to see where that main group or that representative metal is, which column it belongs to, we can quickly determine its charge. And we can do something similar for the main group nonmetals. So for the representative nonmetals, okay, what we can see is all the elements in group 7, they all form a -1 charge. All the elements in group 6, they form a -2. And all the elements in group 3, they form a group 5, they all form a -3 charge. So the way that we can use that to help us figure out the charges on those nonmetal ions, the charge then is equal to the group number -8. Right? So for example, if I look up nitrogen, okay, nitrogen is in group 5. So 5 minus 8 gives me -3 as the charge, right? So when nitrogen forms an ion, it's a -3 charge on it. And it's that simple, right? These are quick ways by which we can do this. And again, we're using the periodic table to help us figure that out.